Till now we have studied spherical rocks freely moving in space, and also we discussed a symmetric rock which is freely moving in space, okay, which are also called as spherical tops or symmetric tops. Now we would like to discuss about a symmetric top that is moving around in uniform gravitational field. Okay, for example, on the surface of Earth, where the gravity is, you can consider as constant over the dimensions of the top, and you can imagine the one point of the top, the lowest point, it is fixed at one point. So that's what we want to consider. But before we do that, let's see what we have done last time. Okay, so we wrote down angular velocity omega in body coordinates. Okay, so we had this expression in the first half of this page, and then we also wrote down expressions for the kinetic energy due to rotation, and then you had this omega I omega, this structure, and we also wrote down this kinetic energy for a symmetric top. And this is one thing which we are going to utilize later in this video today. Okay, so before I take up the top, I want to write down two theorems which are fairly easy. So theorem number one is the following, and I'll prove it, or at least give as an exercise. So we have been defining our inertia tensor with origin chosen as at the center of mass of the body axis. Okay, that's what we did. But let's say you are interested in, for some reason, finding out the inertia tensor with origin not at the center of mass but at some other point, then there is a relation, and that's the theorem about. So the theorem says that the inertia tensor IKL defined with respect to the origin at center of mass of the body, okay, and inertia tensor I prime KL defined with respect to an origin in which with respect to an origin in which is not sounding good, origin, or let me write it, it's not nice sentence, but let me write it anyway, in which, what I mean to say is that you have chosen a system in which your origin is not at the center of mass, okay, in which the from which the center of mass is located at A. Okay, if you are looking at the center of mass, then from the origin it is at a vector, is located at vector A. Okay. Inertia tensor defined with respect to origin and defined with respect to an origin from which the center of mass is located at A are related as following. So if you are looking at KL, I prime KL, then IKL is with respect to the center of mass, and then there is an additional term which is this, where mu is the total mass of the body, and then you have to have other terms. You see there are two indices here, so whatever I write down should also have two free indices, and this is what you'll get. Okay, so if you look at this, this is as if there is a particle of mass mu located at this place, vector A. Okay, so let us prove. Let's prove it. So I will just a second. Yeah. So I start with IKL, which is defining the center of mass. Okay. So you start with that one. Okay. Now let's say this is my rigid body. Somewhere here is a center of mass. We are looking at some point P, and this is my origin O. Okay, and I'm saying this is located at this place where this point is a vector A away from the origin. Okay, so with respect to the center of mass, so this point is center of mass. With respect to the center of mass, this location of the point P is given by vector r, but the same thing from this origin is r prime. Okay, r prime. Okay, so here is the inertia tensor in center of mass, using origin as the center of mass. Now what you do is you substitute this, that your r is r prime minus a. Okay, so your r is r prime minus a. Let me put it in components. So that's what you should substitute in this equation. Okay, and when you do so, you'll generate lots of terms, and some of them will look like what you should have in ik prime, and there'll be other terms which you can combine with whatever you get in using these identities, these definitions. So mrk prime is the location of the center of mass times the total mass. So you will get, you see, this is what this says. This, the entire thing divided by the total mass, is the center of mass. Okay, from this origin. And where is it located? It is located at vector A. So you should get this, right? Total mass times the location of your center of mass. So this is all what you need to use, and you will arrive at to get this, to get your theorem, which is given in equation 1. Okay, so please do that exercise and prove for yourself this relation. Now let me add one more page. Okay. Now I want to prove another theorem, which is trivial. Okay, it says that the potential energy U of a rigid body in a constant gravitational field is same as if it were located at its center of mass. Okay, that's the theorem I'm talking about. So potential energy U of a rigid body in a constant gravitational field is same as if it were located at its center mass. Okay, as if all the mass was concentrated there. Okay, let's see how. So you have the potential energy due to gravitation as minus, I have to sum over all the particles, mgh. Okay, the height of the those particles from some reference origin, okay, which is just minus some summation over all the particles, and let's say r is the vector which tells where the particle is, and all you have to do is take a dot product in the direction of g. So you're looking at the component along the direction of g, which will give you the h times g. So these two are same. Now g is a constant, so I can write down this as okay, this I can take out, and this you know very well what it is. This is just this gives you the location of the center of mass times the total mass minus mu is the total mass, r dot g. R is the radius vector of the center of mass, and if you wish you can write it as minus, maybe I should write it down in the next line, minus mu g h. H is the height of the particle of the center of mass. Okay, so this is the next theorem that we will utilize. So from here you see that this is proving that as if your entire mass is located at the center of mass. Okay, the potential energy is the same as that one. Okay, so that's nice. Now let's go to our goal here, which is to study the motion of a top in a heavy top which is under gravity, uniform gravity. So here I have drawn such a system. Let me write it down here. So we want to look at heavy symmetrical top with lowest point fixed. Okay, we have all the ingredients ready for us. We have already done everything that we need to analyze this motion. So first thing is, let me take some color, or maybe here. Okay, so a few points. The fixed point, we choose the origin, or just write origin is chosen at the fixed point. Okay, so I'm not going to choose origin at the center of mass, which is, let's say, located somewhere here. Okay, that's not where I'm going to choose the center of origin of this body. I'm going to choose the origin here. Okay. Second, because one point is fixed, any orientation is going to be completely described by Euler angles. So Euler angles completely specify the orientation. Okay, so it's a simpler case in that context. Then if you have to choose the choose the principal axes of this body, it's easy to see where they would be because of the symmetry. One of the axes has to be along the axis of symmetry. So one of the principal axes will lie along this. Okay, it is going through the center of mass along this direction, and that is what we choose to be x3. Okay, so that's the one of the direction of body coordinates. So let me write it down. One of the principal axes, I think axis, is the axis of symmetry. and that is what we are going to choose as x3. And you already know that any other, the other two will be in the plane perpendicular to x3, okay, and that is what we are showing here by x1 and x2. So these are your principal axes which will diagonalize your inertia tensor, okay. So good. So your x1, x2, x3 are the body axes. Now gravity is of course downwards here, okay, and center mass, this place is located, okay, from here to there it is L. The distance from the origin to this place is L, okay, starting from here. I don't want to clutter it, okay, that's also good. So from here you'll have a force mu g, okay, that's good. Now one thing is that the origin is not at the center of mass, so my inertia tensor would be different from the inertia tensor which we denoted by I. It will be I prime, and I would like to know what I prime I have, okay, that's one thing. So let me do that thing first. So as we have seen, our I prime KL will be given by I KL plus mu square. No, is it mu? Not mu square, I think it's mu. Yeah, not mu square. Did I write mu square earlier? No, it's correct. So mu times delta KL A square minus AK AL, okay. And what is vector A for me? Vector A is this. Can you guess what it is? It is along the x3 axis, right? So its component along x1 is 0, along x2 is 0, and along x3 it's L. So your vector A is 0, 0, L, right? Now let's see, 0, 0, L. Now if k is not equal to L, if you look here in this expression, if k is not equal to L, then the first term vanishes because the delta function vanishes, and the second term vanishes because it's a product of two numbers, one of which is always 0, right? Because it's either product of first one and third one, or second one and third one, and so forth, and this will be 0. So it's clear that I prime KL is diagonal. So if you move the origin along one of the principal axes, if you keep it on there, it will still remain diagonal. That's one point. And then you would want to know what the diagonal entries are, and I will give you as an exercise to check. It's fairly trivial. Show that I1 prime, these are the principal moments in principal moments of this body. I2 prime, they are still the same, they don't become different, and their value is I1 plus mu L square. Okay, let's check dimensionally. It's moment of inertia has dimensions of mass times length square, which is here also the case, so it's good. And then check that I3 prime does not change, it still remains the same. Okay, that is also fairly easy to see. Okay, that's good. Now we would like to construct the Lagrangian for this system, and I need to know the kinetic energy T for this, and we have already seen what the expressions are. Let's go back. Here if you look at the kinetic energy due to rotation, it's half I1 phi dot square sine square theta plus theta dot square, and the second term. Okay, so let me write that down, and I get t instead of t, let me just write L. No. So my Lagrangian is the following. For the kinetic energy, I have half I1 prime omega 1 square plus omega 2 square, because I1 prime is same as I2 prime, so I can do this, plus half I3 omega 3 square minus the potential energy, right? Okay, now this you can write as the following: half I1 prime phi dot square sine square theta plus theta dot square, okay, plus half I3 phi dot cos of theta plus psi dot square, and then you have minus mu gl cos of theta. Yeah, I think this should be plus. If your height is increasing, that the potential energy should increase, not decrease. So there should be a plus sign here, which you can check by drawing a diagram. You will see, or from here also, from this diagram you can see. Okay, so this is what you get for the Lagrangian. Okay, so now we should analyze this system by looking at which coordinates are cyclic, what are the first integrals, and try to see how much we can tell about this top and its motion based on just by looking at its first integrals. Okay, that is the task which we are going to take up in the next video.